Hi class. Last time we discussed separation of variables in regard to Laplace's equation, where we separated the dependence in terms of spatial coordinates. This time we're going to talk about separation for equations that also involve explicit time dependence. And when we separate in time in particular, we're going to discover the concept of normal modes. So let's take an example, the diffusion equation. Suppose we're interested in the distribution of temperature in some object. That temperature depends on time as well as the spatial position that you're interested in. And temperature diffuses from high temperature to low temperature. And the equation that's satisfied is that the derivative of the temperature at any given point with respect to time is proportional to the Laplacian of the temperature, which is related to how much the temperature varies in space. One nice thing about writing it this way is that in terms of del squared, this is true whether we're talking about 1, 2, or 3 dimensions. As we'll see, it will also be true no matter what coordinate system we use. The constant of proportionality between these two terms is called capital D, the diffusion constant. And if you think about it, you'll see that capital D has the units of distance squared over time. So let's just try the usual separation of variables, but now let's separate the time dependence from the space dependence. So we'll try to find a solution of the form tau of t times a function of spatial position u of x, y, and z. Again, with separation of variables, we're not saying that every solution will be of this form, but what we hope and expect, and in some cases can prove, is that that there's a complete set of solutions of this form, and the most general solution will be a linear combination of solutions of this form. If we plug this form into the diffusion equation, then the time derivative only acts on tau, and the spatial derivatives only act on u. If we then divide through by capital T, the equation we get is here. Tau dot over tau is equal to the diffusion constant times the Laplacian of u over u. But this equation on the left-hand side depends only on time. The equation on the right-hand side depends only on space. Therefore, these two things must be an overall constant. We'll call that constant minus d times k squared, just for convenience. We're implicitly assuming that k squared is positive. We'll see why that's physically sensible in a moment. But all we know at this point is that this is a constant. If we solve the equation for time, we get tau dot as minus d k squared tau, or tau is a decaying exponential in principle, e to the minus d k squared t, and that's why we chose the separation constant with this sign, because in most cases, for example, when we're talking about diffusion of temperature or heat, the temperature decays in time and doesn't grow exponentially in time. Since this is a first-order equation in time, we expect there to be one initial condition we'll need in order to solve this equation. The other part of the equation, the spatial equation, when we simplify, becomes the Laplacian of u plus k squared u equals 0. K squared has dimensions of 1 over distance squared, so k has dimensions of 1 over distance. It's like a wave number. This equation is called Helmholtz equation. Not all values of k will be allowed. In general, k will be quantized, and the exact values of k will be determined by the boundary conditions that are imposed. One way of thinking about this equation is del squared of u is minus k squared u, so k squared isn't, or minus k squared is in that sense the eigenvalue corresponding to the Laplacian with the given boundary conditions. Something very similar happens if we discuss the wave equation. For example, we might be interested in the pressure of air. If we're talking about sound waves, then the second derivative of that pressure is equal to some constant, which has dimensions of velocity squared, times the Laplacian of f, so the time dependence is related. In this case, the second derivative of the time dependence of f is related to second derivatives in spatial dependence of f. So again, let's try to see what happens if we separate out the time dependence and we try a solution of the form tau times u. Again, we're not saying that every solution will be of this form, but we'll find a complete set of solutions of this kind, so that any arbitrary solution will be expressed as a linear combination of solutions of this form. If we plug this form into here and divide by f, we get tau doubled out over tau equals v squared del squared u over u. This only has time dependence, this only has space dependence. Therefore, these two must be a constant. Conventionally, this constant is called minus omega squared. Again, we generally expect omega squared to be a positive real number, so that the right-hand side here is negative for reasons that we'll see in a moment. If we look at the time dependence, then the equation is tau double dot over tau is minus omega squared. That's just the harmonic oscillator equation. Tau is a cosine omega t plus b sine omega t, or similarly in complex exponential form. And this is why we've chosen omega squared greater than 0, or in most cases that's what we'll find, because for the wave equation we're generally interested in oscillatory solutions. So these are solutions that oscillate in time, and therefore omega squared being positive gives us exactly the right form of the equation. There are cases where we'll find that this right-hand side will need to be positive instead of negative, and then there'll be solutions that decay or grow exponentially in time. The spatial dependence then becomes del squared u plus omega squared over v squared u equals 0, which we can write again as del squared plus k squared, del squared u plus k squared u equals 0, where we use k equals omega over v. That has exactly the right relationship we usually expect for waves. Omega then plays the role of an angular frequency, k plays the role of a wave number, and omega is equal to k times v, or omega over v is equal to k. But again, we see that we get Helmholtz's equation. In this case, in the case of the wave equation, this is a second-order equation, so we expect we need two initial conditions, like a position and a velocity, in order to find a unique solution. The spatial part, again, we'll find there are particular quantized values of k squared, or k, that arise from the boundary conditions that are being imposed. Now, these solutions, del squared u plus k squared u equals 0, these solutions of Helmholtz's equations are generally referred to as normal modes, and now we can see why. What we see is any given solution for a fixed k will have a fixed value of omega, and therefore have a fixed oscillatory dependence with a particular frequency. So if you want, these modes represent, like the standing waves on a string, they represent the pure tones, the normal modes of oscillation of the system. So the general solution is going to be a solution of this form. If we either talk about the heat equation or the wave equation, in general they're going to be a whole set of eigenfunctions and eigenvalues, a whole set of normal modes. So for each normal mode, the solution is the form a function of time times a function of space, where there's a relationship between the time dependence and the spatial dependence. But in general, since this is a linear equation, if this is a solution, then an arbitrary linear combination of these solutions is also a solution of this equation. And then we can impose the full initial conditions to determine the values of these unknown coefficients. Fixing these unknown coefficients then from the initial conditions tells us how the function behaves at all times in the future. So this concept of normal modes and the fact that the most general combination, a general solution, can be expressed as a linear combination of all of these normal modes with the appropriate time dependence is a very, very crucial one, and one that's central to everything that we're going to be, or much of what we're going to continue to be doing in this class. You'll see a couple of examples of this when we'll talk. You'll do in-class examples having to do with the Schrödinger equation or the wave equation, and you'll see how this works explicitly.